And if you just press the red stop button or Control-C, you kick it out, and there is no chance to close the socket gracefully in any way. Typically, it's quite problematic to catch this kicking of the program inside the program. I tried it with multiple different ways, but wasn't really successful, and then just gave up, and not enough time to play around too much. So
I have a question.
You have a question?
About the string length method.
Yeah.
How exactly are we supposed to check the size? For console input, for example.
No, you use a debugger. You use a debugger and check the number that drops out. So it will tell you this string has the length 5. And then you take a look at your string and use your finger and count 1, 2, 3, 4, 5. And if it's 5 and 5, everything is right. And if the number are differentiating, then perhaps you need to come up with a solution.
Okay, and so not the code. Perfect. Yeah.
You can, of course, print out the numbers, no problem at all. So I typically switch between using a debugger and just generating some printouts the old way, but you need to check, because there is an error inside there, or not an error, if you might call it this way, but something that can waste your communication quite heavily. Okay?
Yep.
Perfect. So let's get to the next step. So in order for you to work on the exercise, we will slightly go ahead with the socket communication. So we will talk about how to do a communication based on UDP, and we will talk about doing the communication based on IP version 6, and then jump back to the initial basic input regarding distributed information systems, so we can have that covered as well, and I can use that in the exam later on. And then we come back and talk about protocols, and then after the protocols, we talk about the threading problematics and all the related stuff that is inside there. Okay, so that will be the plan for today. So we first talk about the UDP, user datagram protocol. And as I stated yesterday, the biggest differences is that it's not connection oriented. So client and server are not fixed connected. They don't build up a connection that stays alive as long as the communication partners hold up the endpoints alive. When one of the endpoints is closed, then the connection breaks down and everything is untangled. In UDP, this connection is not really done. It's just comparable to the primitive postal mechanism we are using, sending paper postcards around. So the diagram slightly looks different. It's reduced functionality amount. So we have the server that still needs to build a socket handle. The socket handle is bound to a specific address that the server can receive post that is for him or for her, for it. And the receive send methods are also slightly different. As you can see, it's not send and receive anymore. It's send to and receive from. And the close is still the same. Client side, quite similar. We have a socket and no connect, and on the server side, no listen accept or anything. But on the socket side and the client side, we have the socket, and then we send this message to a server or receive data from a server. And of course, the close part is also integrated. So in order to build a socket, what needs to be changed in our current code, needs to be changed in order to have a UDP-based communication. we have to slightly use different parameters in the socket handle construction. So we are still playing around in the internet, but now we have a datagram-based communication, and we can use the UDP IP protocol flag if we want to, or we stick to the 0, and when we stick to the 0, the system automatically decides on the datagram or stream flag here to build the matching one. I would rather go for the first aspect, but you can do whatever you like. So we start from the server perspective because we take a look at the receive from. So we are already bound to a service, and so the bind method is similar to the bind method for the TCP communication. Only the receive from method is different. So the server has generated a socket handle, bound the socket handle to a specific address and port, and waits in the receive from method for messages sent to it. So what does the receive from method need? We need the socket, of course. And as you can see, the socket, the UDP socket is not as easy as the TCP socket to be multi-threaded capable. So that is a problem, but we stick to the multi-threading aspect with the TCP version. So we need the socket, the basic socket. We need, again, the receive buffer and the size of the buffer, which need to be provided. Again, of a decent size, 1 kilobyte or something like that. There again, some flags are possible to be used inside the receive from mechanism. And this is the most important part. We need a sock address struct, an empty sock address struct, comparable to the accept method in the TCP world. Because when the server receives a package from any client, this sock address struct later contains the address information of the sender. So if you're not just receiving data from different clients, but also want to send some feedback to the different clients, you have to use the socket address information here to check or to be used to send a reply to the client based on the UDP mechanism. And therefore, we need this from parameters here. Yeah, and that's basically the idea. So the receive from method receives datagrams based on UDP communication. We need the socket, we need the buffer, we need the buffer size. It's, I think, rather unspectacular. We have some flags, basically the same flags as with the TCP communication world. And we have the address container that can be used to send replies to the client that sent the datagram to the server. And this needs to be taken into account. Again, some return values which have to be checked in order to see if the communication was okay, and slightly different to the TCP world where we had 3 possibilities. In the UDP world, we only take a look at the, or only have 2 return values that are interested. So -1 if an error occurred, and otherwise we receive the amount of data that was communicated. And that's basically the idea. So this can look, this is the way something like your code could look like. And then you have the receive from method, similar, the send to method. We again need the socket to initiate the communication. We have the message we want to send, the size of the message we want to send. So the size is the size of the data inside the character array. So the character array could be 1 kilobyte and the message could be 6 bytes. So it's always nice to reuse space that was allocated. So you could reuse message for multiple communication cycles and just tell the communication or tell the socket, okay, and this byte array only contains 12 bytes of relevant data, and then it will just extract the 12 bytes, send it over the communication network, and then everything is nice and smooth. Send2 also needs an address struct where to send the data to, and that's basically contained in here. And it's again just a socket address struct, which can be used to send the data away in order to target the receiver. So nothing fancy aside from that. You're using UDP, which due to this less overhead, no error connection, no fixed connection, no ordering of bytes supported, needs less overhead and therefore is faster. If you need a fast communication channel, you could support that. Correct. So again, some flags we could use, but perhaps not in this exercise. And of course, there are tons of other access flags that can be used on a socket if you want to. Again, you have to check the return value. So -1 if something went south, and else the amount of transferred data in bytes. Again, in our exercise, we typically don't have the problem to that we don't need to communicate more bytes than we can get out in one chunk. So I had once an exercise that did that, but due to everything needs to consolidate, this was thrown out of the exercise chain. So we want to send some message like hello world, and then send this to our address at a specific port. And that's basically how it looks like. Yeah, and you can use that inside your program to get a decent implementation. This leads us to the next part of the exercise, playing around with IP version 6 addresses. You all know that IP version 4 lost all its available reserve addresses, so we need more IP addresses, and therefore we're using IP version 6. In the TCP world, we only use IP version 6 in the TCP world in our exercise. So we only need to refactor that part of our program. So what can we see later on? What needs to be adapted if we want to support IP addresses version 6? We need to adapt the socket handle, and we need to adapt the bind method, and we need to adapt the accept method, respectively the connect method on the client side. Everything else can stay the same. And that's the nice thing. If you already saw in the exercise that we need to support different server types, so IP version 4, IP version 6, UDP, later on environment server. So it would be good to either bring everything into one project and do something with some properties. So I'm now in state 1 or state 2 or state 3, or you just build different classes which you can use and then activate a server IP version 4 and a server IP version 6 or server UDP version, and then do that. Depends on what you want to achieve and what you like best. So, but IP version 6, let's check what needs to be adapted. We need to adapt something, but first, what we already talked about yesterday and is a repeat, Wiederholung, recall. because we definitely need them in the IP version 6 world, is the use of the INET Python method. And I'm not sure if it was Mac or the Windows world where this method has this naming, INET Python, without the underscore. So camel case, not snake case. Mr. Steiner, you had a question?
It wasn't a question, but it's just the respective version, INET with underscore is the Mac version.
Pardon? I didn't get that.
The INET underscore Python is the Mac version or the Linux version.
Okay, perfect. So this must be Visual Studio style.
Concerning questions overall, I think the
Machen Sie auf Deutsch.
The hand paper, the Anleitung with the song is quite good. We just had some programming problems which can't be solved by the papers or the PowerPoints. Therefore, the lecture or the tutor is great. So, like the socket type, which isn't available in all compilers, which just is an int. We didn't know that, and that was
but I stated that yesterday.
Yeah, but we, of course, we listen to all, but we can't remember all.
Yeah, that's right.
Another thing was the setup of Sigwind for some guys. That was a little bit difficult because there was then no configuration scheme, and the CMake profile was missing, and so on. So it was not the problem.
It was the setting up of the environment that took up some time.
And
but that's the reason why we have tutors, and that's the reason why I'm in the exercise. If you have something like that, problems you are target or you're working on, just give us a call. We help you out. We know what needs to be done. Okay, so even if it's not around the topic itself, it's like setting up the system. Just call us, and if you have problems, and we are happy to help. Nothing is more boring than sitting around 4 hours and doing nothing. Okay, so having discussed that, let's come back to the content. So we definitely need the INET Python version of the conversion of the human readable IP address to the network byte order computer readable network address when we want to use IP version 6, because then we need to change the protocol family. In IP version 4, we had AF Enet, and when we use the IP address 6 version, we use AF Enet 6. And this is definitely important if you change that, because if you change that, then the size of these two is changed, or the method assumes that the size of these two void pointer or this character array and this void pointer has the matching size. And this is really, really, really important. Otherwise, you are getting errors that are not nice to find and not nice to interpret. Aside from that, INET Python has some return values. So -1 if something really has gone bad, and 0 if the IP address could not be converted, so you made a mistake on that side, and 1 if the conversion was successful. So if you have an IP version 6 address, you can use that and use INET Python to convert that into something that the system can use to trigger and target a communication partner. So this is the way this can be used to address something. And of course, the same method works the other way around. reading in a machine readable network address and converting it into something we can read. And again, you have to be extra careful which protocol family you are announcing to be used, because the destination size and the address size are different. In the conversion size here, it's not really problematic because you are reading, and the character size here, it's problematic because you read in the address here and write something in the address here. So if this one has the wrong size, you will be writing in some other person's memory space, and this typically doesn't go out without any harm. So that's basically it. We need the address family, we need the socket address, or we want to target, we need the address length, string length, which can be used, the character array of a decent size, and the system returns null if something has gone wrong, and the character array, a decent character array if something was worked correctly. And what you can be sure of, that this character array is null terminated aside from that. So this could look like this way. We have an ANF address family. We have a version 6 address available, and then we can use it, and it will be stored, the address will be stored in this character array here, and then can be used and read and written and whatever you want to do with it. The thing that you can already see here is that the address struct slightly differs if you use the IP version 6 mechanism. So the address struct, there is an address struct for IP version 4, there is an address struct for IP version 6, and at some systems, there is a generic address struct that is capable of supporting both worlds. But you have to be sure that it is available at your system, and it can be casted into socket address for version _in, which is TCP IP version 4, and socket address _6, which is IP address version 6. And therefore you could use one that supports both worlds. But this is just something you might want to try out, but not necessarily do need to try out. This brings us to the methods that need to be adapted. Short look at the clock, 9:34, and we make a break now because, as I was told yesterday, talking for 90 minutes reduces the amount you take in. So it's no wonder you dropped the integer remark regarding the socket handle. So we make a 5-minute break now. And after 5 minutes at 9:40, we return and talk about what adaptations need to be done in the socket construction, socket handle construction, the bind mechanism, and the accept and connect method to support IP version 6. See you in 5 minutes. Okay, back in business. We were left when we were talking about the socket construction, how to build a socket handle that is IP version 6 capable. And that's quite easy. All we need to do is choose a different address family. Instead of using AF eNet, we use AF eNet 6, and the rest stays the same. So that's basically it. And after that, the socket is capable to work with IP version 6 mechanisms. The bind mechanism is you have to use an adapted IP version 6 address struct. So we already saw that at the example of the eNet NTOP and the other way around. Or we can use a generic storage version of the address struct if we wanted to. But typically, most of you want to use the IP version 6 version of sock address underscore in. So and that's basically attaching a trailing 6 to the socket address struct. It's slightly larger, has slightly more content, and sometimes in some system this length information is missing, but we are typically only interested in the property, the family, the port, and the address. So we are manipulating the family, the port, and the address, similar to the version 4 version. That's basically it. We use the address family AF eNet 6, just like the socket handle construction. The port stays the same because that has not changed by using the IP version 6 addresses. What has or what needs to change is, of course, using the IP version 6 address and using the eNet PTOP and NTOP, PTON and NTOP methods to convert the human readable IP version into something the machine can use, and the other way around if you want to print out the address of the client that contacts you. So how does the IP version 6 address struct look like? Basically the same as the version 4, just with the trailing 6. And so basically the socket address struct will be filled with the family information, address family information, with the port information, and the address. On the server side, we use, again, in-address any, and there is a version 6 of this in-address any, in6 address underscore any, or sometimes in6 address underscore any underscore init. So there is something on every system, but it may sound slightly different. So this is the server binding address part, and the client one differs just by not using the in-address any part, but using the, do we have an example on that side? I think we have an example over here, right. So this is targeting an IP version 6 or using an IP version 6 to generate a network readable address in here in this one. And then you can use that to target a server. Right, so this is how to set up the server, and the other one was how to target and connect to a server. So continuing with the accept method. So now we have a version 6 socket handle. We have bounded to a version 6 address. Listening stays the same, so we set it into listen mode. Then it starts listening for connections, and we wait for incoming connections in the accept method. And of course, inside the accept method, we need to take or make sure that when we are playing around with IP version 6 addresses and we want to grab the client address, then we need to provide an IP version 6 client address struct, and then we can use that and extract that later on to print out the information about the connected client.
A small notice here was, which was also found in the exercise. I did it exactly the same way with int size, size of, etc. I put it with the and symbol for writing in it, so it's giving it the address of the field. Then it wanted a typecast all the time, and so I did the typecast not in the argument. Instead, I differed the int into the specific of this size type. So it's like a sock address size underscore t, something like this.
But that typically is dependent on what library you're using.
Okay.
So, and that's of course, when you do something like that, it's basically the same problem with, and that's the reason why I will choose to convert it into something that the Linux system supports, that brings in the same problem you were complaining about with the socket handle that pops out here. So in some systems it's int, in the Windows Visual Studio world it's socket, and somewhere else is something completely different. So when we state here this struct or the type you were just mentioning, then it works nicely on the Mac platform and perhaps Linux, but all the others are, okay, I don't get this type. This type is not declared on my platform.
Is it better to typecast it?
It makes no difference. A good compiler just kicks it out, and that's completely irrelevant. So a good compiler will optimize in the background everything we are doing stupidly anyway. So it's just something, what is necessary is that you can read your code, and that the others that are working in your team can also read your code. So that is more important. It's more important to structure your code in a way that everyone in the team and the company does it the same way. So you can exchange code and read your code from your partners. That's way more important. Okay. Right. So the accept method, aside from that, everything else stays the same. You just need to make sure that you have the right size of the address. The connect method on the client side, again, an example how to state an address that is targeting an IP version 6 address. So you can have a decent large IP version 6 address, or you can use column 1, which is the equivalent, as you know, for localhost or 127.0.0.1 in the IP version 4 world. So that's basically it. And you can catch your IP address by questioning your operating system IP config on the Windows world, and I have no clue what's on the Mac world, but I think you already know that. So that's basically the idea. You need an address that is capable of supporting IP version 6. You need INET Python to convert something that we can read into something the machine can use. And then you can use this address to connect to the server, and then everything else will fall into place. And then you can connect to your IP version 6 server. Next step will be socket optimizations, but as I stated, I want to first have leap backwards to the theoretical part, because I need that later on because if we just have programming stuff, this is typically problematic. I need some theoretical questions as well. So let's see. This brings us back to the general design goals of distributed information systems. So we already talked about the resource sharing, thought that multiple clients want to use the same server. Just think about Amazon, where imagine when you wouldn't share the resource of the shop of the Amazon, then of course it would not work as the way we already know it, love it, and use it every time or all the time. We talked about the transparency aspects and that it is good to hide the transparency or to integrate transparency for the normal users. And sometimes it's not so good to hide everything because perhaps they think that their computer is broken when there is just some background server that is not working appropriately. But nevertheless, most of the time, transparency is a good thing. Hide complexity for the people that don't need to know about the complexity and think that everything is nice, fine, and soft and easy. But we all know that this makes life complicated. Right, this brings us to the next aspect. The next aspect about distributed systems is openness. And openness targets the goal that you want to integrate, extend, or be used by other systems. And when you think about a distributed system, this is of course obvious because we have different components that reside on different computers, and somehow they have to work together. And in order for them to work together, they cannot hide every aspect of their essence. They need to tell us, okay, which API are you using? Which communication mechanism are you using? Which protocol are you using? And therefore, openness plays a key role in distributed information systems. So what we need is that the components that are part of the overall system they all need to rely on standard rules. They need to so this aims at they need to state how they work. So they need to provide an API, they need to provide an interface, they need to provide knowledge about how should the data be integrated into the interface. What kind of interface is available? So the openness also, this is the idea behind the openness, and of course the openness therefore needs to specify, or the systems need to specify how their interfaces look like. And specifying how their interfaces look like, of course, needs to be based on some syntactical rules, and the way how it is used also gives some insight into semantics of the service, of course. So if you have an add contract, then you know, okay, the system is capable of working on contracts of some kind. But the add contract interface aspect, of course, needs to be stated in a way that we as system generators, system builders, are capable of using this service and integrating it into our system. So we need to know the format, the content, and the meaning of the messages. And of course, all this needs to be stated through one so-called interface definition language. So the system needs to tell us how to work with it. When we just use one programming language, this is typically quite easy because we just get an interface and we know, okay, when we use the methods in the interface, everything is nice and fine. But in a distributed system, of course, we have different system parts using different programming languages, who are running on different machines. So the complexity of telling my partner how I work is increased, and therefore in the distributed world it's not always so easy as when you have when you're using the same programming language and when you have some logic hidden behind an interface. and you just use the interface, build a dynamic object out of some implementation of that interface, and then you can use it. But in the distributed world, things are slightly more complicated. Typically, when we have these interface definition languages, they state what kind of functions are available, what type of parameters are necessary to use the functions, what types do the parameters be of, what kind of return values are provided when I use a specific function with some specific parameters. So what drops out, what type of object is this, and of course, what happens if something goes wrong. In general, you can say that interface definition languages define what can be done, but do not share how it is done. But that's basically the idea of an interface. You just tell your partner, okay, you can use this side of my system. How I do it internally is not of your business. And this access port that is described in some way. It can be DNORM, or it can be interface description, it can be a SOAP interface, it can be a REST interface, it can be a remote method invocation, it can be a remote procedure call, it can be a simple socket. And you need to somehow state that, express that, so others can use the system. And in distributed system, this of course is way more important or way more complex than just using interfaces in programming languages. This brings us to the next aspect. A thing that is also quite important for distributed systems is the key design of scalability. So you have typically you build a system, then the system grows. Sometimes in functionality, sometimes in more users using your service. And therefore, you need to scale up your system. You scale up in functionality, you need to scale up in size, you need to scale up in velocity, you need to scale up. So there are multiple scalability dimensions. And therefore, this is also quite important. Imagine you build a system that is only for your company, that should be used in some part of your company, and suddenly you realize, hey, this is a nice feature, we could sell that. So, and now you need to scale it up. It needs to leave your home turf and be used in different companies and in different administrative levels. And therefore, this something develops in a direction which you didn't know in the beginning, makes scalability also quite complex and not straightforward. And scalability is one of the biggest problems, because typically this is done under time pressure, and then things always go bad. Time pressure is one of the biggest problems. So scalability is defined when you take a look at the literature. Of course, all of this is extracted from the foundation literature regarding distributed information systems. And scalability, of course, then also has a specific definition that is part of the hardware or software. So this also is targeting the hardware, but of course, we are not interested in the hardware. We are currently looking at it from a software perspective, that enables the extension of the system regarding future requirements. And of course, future requirements is something you don't know. So the system you build can work nicely in your company, and someone says, okay, let's sell it to other companies, or it stays in the same company forever. And that's fine. You did your job, you did it well, it's working nice and smooth. But it can happen that suddenly it starts to grow. And typically software in companies starts to grow because you build something, then the target changes, you have to adapt the system the system changes and these extensions, if you don't envision them in the beginning, tend to ruin the design of the system. But that's just a remark. You will see that multiple times in your work lifetime. So what are the dimensions something can grow? So the size can grow. So the size of the functionality, the size of the system, more users are supported, more resources are integrated, not only database A, but A, B, C, D, and something in addition. And of course, when the system grows, it should not degenerate in performance. It should always work smooth, reactive, stuff like that. And this at a certain size gets complicated. Another aspect is geographical. So what happens if the system not only stays in your company, but you eat a competitive company and integrate that into your company? Suddenly you have an outpost in France and in South America and in Asia. And so the system also not only increases in size in one of your servers, but also geographical. Suddenly you need to support way more distributed aspects. And something that is also not on our radar most often is the administrative part. What happens if parts of the software you are using are not under your control anymore? You are using a part, a service from someone else. And what happens if the service changes? If the ideas and work ideals of the company that hosts the service are not the same as your company ideas, 24/7, 365 days, and all this time. Everything stays online all the time. And this is problematic. So let's talk about what can be problems if you scale in size. So these are aspects that are problematic. So if you have a central service, this can be a problem when you grow in size. So when you have a central service, a server, a cluster that is only this central service is responsible for a specific service, for a specific aspect in your system, this could become problematic. So it's the bottleneck. Everything needs to go through that service. With 100 users, no problem at all. 1,000 users, 10,000 users at the same time, things get hairy. So this could be a problem. Centralized data, if you have all your eggs in one basket and the database is accessed by multiple servers at the same time, by multiple thousands of clients at the same time, this could be problematic. Even if especially so if the clients are calling your service from different continents. Centralized algorithm, something that is very, very bad in this distributed system. So when you have to make a decision in your system, and in order to make that decision, you need to know the complete state of the system. That is meant by centralized algorithm. So you decide to switch from state A to B, but in order to make that decision, you need to know the whole state of the system. This is okay for small systems, no problem at all. But in a distributed system, this is nearly impossible. Because before you get all the information from all the systems that are part of your overall system, before they arrive and help you to make the decision, situation has already changed. So you're making the wrong decision based on old facts. So these are aspects in a distributed system that could really cause you a headache. Scalability problems are regarding the dimension geographical. Of course, you have to take into account the response time behavior. Locally, this is very fast. Globally, the response time is slow. So you can ask your neighbor, if you were sitting in a lecture room, you could ask your neighbor and you would get a very fast answer. But on a global scale, you send an email and you wait and you wait and you wait and you get an answer. So this can also be an aspect in the system. Communication behavior. In a local system, you can communicate synchronously. You can target your communication partner and wait for the answer. But if the answer takes up time, your system is idle and nothing else, or it does not do any jobs. On the global scale, this needs to be done asynchronously. So you query something and do something else. But of course, this query something and do something else increases the complexity of the system. So when you do something else while you're waiting for an answer, what happens if you finish that job, start another one, wait for the answer, or when you're working on the next job, the answer is returning, and you have to decide, okay, do I stop what I'm currently doing and working on the initial work package, or do I continue the work package and then work on the next work package, or is there a higher priority work package? So things are getting more complicated as soon as you start doing things asynchronously. So that's also the reason why when we integrate multi-threading concurrent behavior into a system, typically the system complexity increases by factors. And this, of course, also is a problem when you scale up the system and go asynchronously in the communication behavior. Reliability locally, that is high. So in a local environment, you can, without any problem, use UDP communication to really go fast. But when you want to use that and go from Europe to South America, for instance, then there might be some packages getting lost, and the order of the packages might not be as you expect them to be, and stuff like that. And of course, it can happen that the communication is shut down by some external environmental element. So a Brazilian network provider just decides, okay, we are now doing some maintenance, and shuts down the communication. So, and then basically that's it for you. You cannot reach your communication, the system you are trying to reach. Discovering services locally, you can broadcast. Globally, of course, you cannot broadcast, and you will not be allowed to broadcast. So globally, you have to really know what you need to do, and therefore this might change. So local systems typically behave differently than local systems. Global systems behave differently than local systems. And on a multiple levels, and you just have to be aware of that. And if you already know that you will be scaling up, not only in that your company is working in different countries, different continents, then you can envision that when you design your system. But it gets problematic when you are designing a system that should work locally, and suddenly you are told, and now we just go global. And then you have to rethink. And when something like that happens, forget the factor multiplied by 2, the time you need, multiplied by 10, 20 or so is more relevant if you can get that, because then you really need to redesign your system. Administrative is also something. If you switch from having your own infrastructure to let's outsource something and use something from a different company, of course, this is typically not for free. So you need money to use the resources. Of course, when you outsource some aspects to different companies, you always have to take into account the security. So do you really want to store your data in a Cambodian cloud server or not? And that needs to be taken into account. Ideology is also something. We typically think that the whole world should work. I have the same work ideology as we have. But if you start to work with people from different continents, you realize, okay, they have a different idea how the world should work and could work. And this could be sometimes problematic for certain deadlines. And what you need to keep in mind is that the trust typically only exists with your own domain company. And typically you mistrust different other domains and companies, and perhaps you must mistrust because they have different ideas, they have different feelings how things should work. And this, of course, needs to be taken into account. So for the scaling dimension, I have some techniques, extracted some techniques that are mentioned in the books that can be used to cope with the scaling problems. So one of them was, or the biggest problems I told you was the centralized algorithm, that you need overall knowledge to make a decision. And of course, the solution is that simple: don't do that. So in order to have your system working, you cannot support, if you want to be scalable, the idea that you need to know everything. And if it is possible in your system to discard that, then you don't have the problem of a centralized algorithm. So you need decentralized algorithm, that is called in the system. So we have no node. Node is part of the system that needs complete knowledge over the system state. And if you don't have that, then of course the centralized algorithm problem is not affecting you. And the nodes should make decisions only based on their local knowledge. Of course, this is sometimes not as easy as it is stated. And of course, you should try to keep the system alive. If one of the nodes fails, bring up a backup node, compare the values of some redundant nodes, so you're not calculating it with one node or one aspect of your system, but you're using 3 aspects of your system, and you compare the result. If they are all the same, everything, or at least you can be rather sure that everything is okay, because every 3 can have the same fault at the same time, which is not impossible, but which is unrealistic. And therefore, if one provides different information and the other 2 are providing similar information, you can think, okay, how realistic is it that the one is still working and the other ones have the same mistake? So you see what this is aiming at. And something that seems to be rather funny, but it really isn't, is you don't need a global clock. Or you should not need a global clock. So what is this aspect? The idea is that all systems are synchronized, that they are all using the same time. This is quite simple, or this is simpler if you are building a system that is running on one server in your company. But as soon as the system is split up and set up in different continents, then of course these servers stand in different time zones. And these servers are managed differently. So what will happen is that there is a time drift. And then, of course, if you don't need to know when an event has occurred exactly, then this is not a problem. But when you think about Aktien sind trading stocks, thanks a lot. When you're trading stocks and you're doing, okay, I want to buy them now and I want to sell them now. And typically the time when you buy and sell is quite important, or it can be quite important, because then the stock price drops because you're selling quite a lot of them. You see that someone is selling quite a lot of them and you want to get rid of yours as soon as possible. Or when you are buying something in an auction, who gets the bid, the first one, the second one, or something else, computer games. You're sitting in front of your computer game, you're aiming with your rifle at an opponent, you trigger, and then you're shot. But you, of course, say, I shot him first, or I shot her first, I shot it first. Because I pulled the trigger and I wasn't killed then yet. And of course, the problem is that the person that is also targeting you did also shoot, and the system has to decide who shot first. And therefore, the system needs to maintain something like an event queue, a global clock, in order to decide, okay, who shot whom, and or who got the resource first. Something like that. And my kids typically are quite annoyed with that feature because they always complain, but I did shoot him first. But of course, this is just a perspective of them, and the other one has a similar aspect. Okay, using asynchronous communication, something we already talked about. So the technique waiting synchronously or working asynchronously. Synchronous means I'm the client, want to use something from the server. This typically needs time. So x-axis is time. So I do something, I query the server needs some time to calculate the answer, sends the response, and then I continue. And while the server is doing something, I'm actively waiting. I'm blocked. I cannot do anything else. This, of course, is okay if this is quite fast. And if this takes more time, then the client should work asynchronously. So the client triggers a query, does other things, and then the response pops up. And of course, as I already stated, asynchronous mechanisms, concurrency bring complexity, because you then have to decide, okay, what happens exactly here? Should I stop doing this, or should I first continue doing that and then later use the response? Or did something jump in the queue and is even higher priority? So complexity is increased. But nevertheless, that's the difference between synchronous and asynchronous. And of course, life is not as easy as the diagram we just saw, because we typically don't have two-tier architectures. So tiers are layers. So typically we have a browser, we click something in the browser, then in the background something on the web server is done. The web server triggers the database, queries some new data, builds up the new dynamic web page, and then returns the result. And as you can see, these layers can be rather deep. So there is a ravine, keine Ahnung, die Schlucht, opens up a huge time gap. So if you're working asynchronously, the application server does not have to wait that long, but the user interface has to wait that long. And this can be problematic. Also, useful scaling techniques can be dynamic and useful distribution of tasks between client and server processes. This means something like fat versus thin client. So if you have a thin client, you just have a user interface and all the work is done in the background. If there is not much communication necessary, this works like a charm. The problem is if there is much communication to be done to the database section down here, then of course this gap opens up. and the client has to wait. And therefore, sometimes it does make sense to bring in some more application logic to the client side, making it a fat client, fat in functionality. And it can do most of the stuff locally and just now and then needs to trigger the database. And so depending on what you want to achieve, you can either choose this approach or you can choose this approach. Or what is also possible is to dynamically adapt that. So when you're using a terminal in your house, you want to use this way. When you are using your smartphone, you perhaps want to use it in such a setup. And when you are inside your car and really have some infrastructure and really can do something, you can use a setup like this. Or that's basically the idea, and this can be done dynamically. So the system realizes, okay, I have not much computing power, let's reduce the functionality and use the functionality of the server side. Or when I'm in a smartphone, okay, I have space, I have processing power, I can beef up my system. And this can also be done dynamically. Another aspect for the scaling techniques is replication, which sounds nice and smooth and easy, but which really brings in a red tail of problems. So the idea of replication, I think, is rather simple. So you have a database which needs to be used by your system. And we already heard that having only one database is a bad idea. So the idea of the replication is just make a replica of this database. And now we have two databases. So we can move all the client requests to two databases and now make four databases. So all the client requests go to the four databases. And now we can even set up the database replica in different continents. And then the load balancing is working easier and nicer, and the response time is increased, and everything is fine. This is true as long as you're only reading data, or not even then, it's only, but if you're only reading data, this is not a problem. But as soon as one of these nodes of this client is changing the data in one of these databases, then the problems start. Because then you change the data in one database. And of course, this change needs to be also represented in all the replicas. And then things really go south, because the idea of the people and often also of the management is that, of course, it's easy to just do the change in all the databases. But there are books only targeting this problem, because there is not one change at an instance, there are multiple changes at an instance, and sometimes a change means in database replica A means that someone that is reading the same content in replica B at the same time, it gets the wrong output because it already has changed in replica A. And how do we cope with that? And the database replicas are not sitting side by side. They are distributed by tens of thousands of kilometers. And at the same time, they are accessed. So what do we do? And we cannot, one of the main problems that arise is the consistency of the replicas. And the consistency problem is a huge one. And as I said, there are books about how to maintain or try, you cannot maintain, you try to maintain the consistencies of the replicas as best as possible, but you cannot keep them up to date all the time. It's impossible. It's just physics just kicks us in the back. That said, let's check the clock, 10:24. I think we can stop here. And as I thought, we will not be talking about protocols and socket optimization today. So socket optimization, protocols, and threads are the topics of next week's session. But I think we have enough to do in the exercise to get the 4 hours workload done. Again, if you have questions, if you are not sure you're doing it right, trigger us, please. And then we help you. If we help you get on the right track early in the stage, you can easier keep your source code nice and clean, and the restructuring effort will be less problematic. Okay. That said, I will close down the call in a minute or two. Thank you for listening. Thank you for watching. Thank you for